Number 69, integrated concepts. Letter A. A large electric power facility produces 1,600 megawatts of waste heat, which is dissipated into the environment in cooling towers by warming air flowing through the towers by 5 degrees Celsius. What is the necessary flow rate of air in cubic meters per second? All right, so first, here's our little power plant, right? The power plant is producing energy at a rate, it told us, of 1,600 megawatts. That is the same thing as saying 1,600 megajoules per second. I'm going to break up the watt into joules per second. You know watts are units of power, and power is equal to energy over time. All right. So also what I can do is just get rid of the mega for right now, right? I could just convert this. Why don't we just get that out of the way? So this would be 1,600 basically times 10 raised to the 6th joules per second, just to get it out of the way. All right. So what I'm going to do, so now what they're saying is that the power plant is basically producing, right, this amount of energy per unit time, and we have to figure out now the flow rate of air that goes, they say through the towers, I showed it on top, whatever, it doesn't matter. We got to find the volume of air now per second that we need to have moving through the towers in order to only warm up that air by 5 degrees Celsius. So notice they give you a rate here in seconds, and they ask for a rate in seconds. Okay. Basically, then what that means is I can actually ignore those seconds throughout the problem because they're going to be consistent. If I use this energy in my calculations, and I know that this energy is per second, then if I can somehow take this energy and convert it into a flow rate or into a volume, then I can simply say that that would be the volume per second. All right, so let's do that. So we first realize that the air is going to be warming up 5 degrees Celsius. So we're thinking about, well, air warming, okay, I got some heat here, I got some energy, right? I got a temperature change. Maybe I should use this formula over here on the right-hand side. That would be a good start. So this says that the heat energy necessary to be gained or lost, depending upon what you're calculating, is equal to the mass of the object that's changing temperature multiplied by the specific heat of that object multiplied by the change in temperature of that object. Now they told us that the temperature change is going to be 5 degrees Celsius, so we know delta T. We also know the energy, right, that's being put into this air, so to speak, per second, okay? But remember, I'm going to use just that energy, so I know Q. What I can do then here is solve for M. You might say, well, wait a minute, we don't know C. Well, remember, that's a constant, all right? We're talking about, what are we talking about? What's changing temperature? Air. So what do we need to know the C of? Air, all right? So solving this for mass of air, I'll call it M sub A, that would then be equal to Q sub A over C sub A delta T sub A, right? This is all for the air. So the mass is, so the energy being absorbed by the air basically is going to be 1,600 times 10 to the 6th joules, divided by the specific heat of air is about 721, and multiply that now by the change in temperature, which is 5 degrees Celsius. Okay, so now all we need to do is now calculate this. Let's just move this on over to the side. You can look up that value for air. That's the specific heat looked up in the table. So we get 1,600 times 10 to the 6th divided then by 721 times 5. And this is about 4.44 or so. How many decimals am I going to put there? 4.44 times 10 to the 345. And that's in kilograms. All right, now that is not the answer, but that's one step closer. So if we were able to find the mass, how do we find the volume? You have to know the relationship, right? That's through the density. So the density of an object is equal to the mass divided by volume. Volume is then equal to the mass over the density. So simply plug on in. Your mass is about 4.44 times 10 to the 5th kilograms. The density of air is about 1.29, right? That you can look up as well. That's going to be kilogram per cubic meter. And now when we calculate this, right, we just divide it by 1.29. And this is about now 3.44. So let me just move this on down ever so slightly. So this is going to be then, I'll just put it underneath actually. The volume then of the air is going to be about 3.44 times 10 raised to the 5. And that is in now cubic meters. Okay, so that's the volume of air. Now that's the volume of air, right? Let's just go back and make sure everything makes sense. This is the volume of air that's necessary to basically to absorb this amount of energy, okay, and only raise this volume of air's temperature by 5 degrees Celsius. Now, if this is the amount of energy being produced per second, well, then this is the volume of air that's necessary per second. So actually, all you need to do now is just put a little per second sign down there. And that's it. That's A. And then B, is your result consistent with the large cooling towers used in many? Sure. Okay, guys, thanks for tuning in. Please remember to subscribe. We'll see you next time. Take care.